Welcome back to Precalculus. Today we're in Chapter 2, Section 4, talking about functions, notation, and graphs all at the same time. Okay, so let's dive right into some vocabulary here and talk about functions. So a function is a relation that pairs each element of the domain with exactly one element of the range. So basically you can't say an element of the domain goes to two different places. So if you look right here at this first example, we call the teachers the domain and their room numbers the range. Is there any teacher that's being asked to teach in two different rooms? Doesn't really make much sense. No, there is not. So this is, in fact, yes, a function. Okay, because each one teacher is mapped to exactly only one classroom. Okay, so now looking at this function and set notation here, is there any x values that have two different y's? Well, if we look right here, and right here, the number -2 is being told to go to 4 and also go to -3, so this is not a function. Okay, and that'll make a little more sense as we take a look here at the vertical line test. So the vertical line test, otherwise denoted as VLT. Okay, a given graph is the graph of a function if and only if every single vertical line intersects the graph at most once, or at most one point. Okay, so we look right here at this first example and we're like, oh, well, I can draw a vertical line like this, any vertical line. And if it's going to hit the graph more than once, it's not a function. So no, this graph is not a function. Now this one is an equation, so we should probably graph it. Okay, so if we graph this, we can graph it a couple different ways. I'm just going to do it by plotting some points and knowing that what my square root graph is going to look like. So if I plug in the point 0 for x, 0. 4 minus 0 is 4. I'm going to get 0, 2. Yeah, I can plot 0, 2. That's a pretty easy one. And I'm going to plot 4. If I plug in 4, square root of 0 is 0. So 4, 0. Now I know if I plugged in 5 or something like that, like 4 minus 5 would be negative, and we're going to get an imaginary number. So anything to the right is not going to exist. And knowing that my square root graph is going to be an arc, I know it's going to look like this. Okay, does that pass the vertical line test? Any vertical line I draw, I'll use my pen here. Any vertical line I draw is only going to hit the graph once. So yes, this is a function because it passes the vertical line test. Okay, let's talk a little bit more about domain and range. So the domain, or the x values, can be found with the help of a vertical boundary line. Talk a little bit about vertical boundary lines and horizontal boundary lines here in a second. Okay, those represent all of the x values. Okay, if you look at my graph here, a vertical line represents all of the x values, the values on the x-axis. The range, aka the y values, can be found with the help of a horizontal boundary line. Horizontal boundary line to represent the y values. And I'll do the same thing with my pen here so you can see on this blank graph all the y values. Okay, so we're being asked to determine the domain and the range of this function using boundary lines. Okay, so without getting too much into graphing, just recalling from Algebra 2, this is a parabola shifted down 3. Okay, we could do all kinds of plotting points and stuff, but shifted down 3, over 1, up 1 in each direction, over 2, up 4 in each direction. There is our parabola. Okay, so if we look, and you're going to have to watch the video to understand this, the domain, what vertical lines are going to hit this graph? All of them, because the graph goes forever left and forever right. Okay, so all of the vertical lines are going to hit it. So we say our domain is -infinity to infinity in interval notation. Now for range we use our horizontal boundary lines. Well, horizontal lines aren't going to hit the graph down here. They're only going to start hitting the graph right here at -3 and going up from there because the graph goes forever vertically from there. So we want to include negative 3, so we use a bracket, and all the way up to infinity. And I'll do that again so you can see it. From negative 3 all the way up to infinity is going to be our range. Okay. The implied domain is the set of all real numbers for which the function represents a real number. Okay, so for rational expressions, the domain will exclude, remember rational means fraction, the domain will exclude any input that causes a denominator of 0. You probably remember that from last chapter. Anything that causes division by 0 is bad. Okay. For square root expressions, the domain is going to exclude, you're probably getting ready just to jump out of your seat and say it's going to exclude anything that makes underneath the radical negative, that create a negative radicand, anything underneath the radical. Okay. So let's look here. Let's find the domain of this. This is a rational expression, so we don't want division by 0. We care less about the numerator. We only care about the denominator. So some quick math says x plus 3 cannot equal 0, so x cannot equal negative 3. So how we write that in interval notation? Without drawing number lines or anything, negative infinity to negative 3. We don't want to include it. Union with everything after that, negative 3 to infinity. Okay, let's do the next two together. So now here's this radicand, 3x minus 2. Well, we know that 3x minus 2 has to be greater than or equal to 0. So add your 2 divided by 3. X must be greater than or equal to 2/3. So writing that in interval notation is anything from 2/3. We're going to use a bracket because it's greater than or equal to. Greater than means going to the right, so we're going to go to infinity. Okay, last one here. I don't see any kind of rational expression. I don't see any variables in the denominator, and I don't see any variables underneath the radical, specifically an even radical. Okay, all I see is some exponents and whatever, but because there's no variables in the denominator and no variables underneath an even radical, I know automatically my domain is negative infinity to infinity. So what I want you guys to do is I want you to try these two more difficult questions on your own. Okay, notice we have a rational expression and the bottom is also underneath a radical. Okay, so see if you can find the domain of this problem. And then see if you can find the domain of this problem. Now I'll give you a hint on this one. They try to French this one up and make it look a little different, but this one is actually the same type as this one because the square root of this whole thing is just the same as the square root of 3 over the square root of 7 minus x. So go ahead and pause the video and see if you can find the domain of these two functions. Okay, the second to last thing we're going to talk about today is function notation. Okay, and function notation just means f of x, and that's, you've probably learned it as being f of x is the same as y. Okay, where we call our x, just the x itself is called the input, and the y is called the output. Okay, but f of x is the same as saying y. Essentially, you see a little diagram here. We're inputting an x into a function, f, and it's going to shoot out some y. Okay, so here's an example. If we plug in 2, so your g of 2 says plug in 2 into this g that's given to us. G of 2 is equal to negative 2 squared plus 4 times 2 plus 1, which is going to be negative 4 plus 8 plus 1, which is 5. Okay, so on this graph right here, the point 2, 5 exists. That's what you can take away from that. Okay, g of 3x is the same as, you're just going to take 3x and plug it in, so I'm going to do just that. G of 3x is equal to negative, take your 3x and square it, plus 4 times 3x plus 1, it's going to be negative 9x squared plus 12x plus 1. Can't really be simplified any further from there. Okay, same thing here, g of t plus 2, I'll go down here where I have some more space to write, but g of t plus 2 is just taking that t plus 2 and plugging it in everywhere where you see an x in G. And we could FOIL all that out. If you want to FOIL it out, we can go ahead and do that. No big deal. So what do we got here? We got negative t squared plus 4t plus 4 plus 4t plus 8 plus r1. If you simplified all that out, you would end up with negative t squared plus 5 as your final answer. Okay, let's slide on down here and take a look at the graph. Okay, so this function, we're calling these dots a function. We're not connecting the dots, they're just discrete dots, is called h of x. They want us to find the domain. So the domain is all of the x values. Okay, and because it's discrete and they're all just points, it's not a continuous line, we can't write it in interval notation. We can only write it in set notation. So our x values are negative 9, negative 4, 1, this one is 6, and the last one is 11. So the x values. Okay, I'm going to go ahead and jump down to do the range since domain and range kind of go together, so that's question B. So the range is just asking for what are the y values? Smallest to biggest. I like to write smallest to biggest order. So the y value of these 2 points is the same. I'm only going to write it once, so negative 3. The y value of these 2 points is the same, so I'm only going to write it once. 2. And the y value of this point right here is 6. Perfect. Okay, so there's our domain and there's our range. Now we're being asked to evaluate this function at x equals 1. They're saying, what is h of 1? When you plug in 1, what do you get out? 1 is the input, the x. What is the output? Y. Well, if we plug in 1, we get out a y value of negative 3. Plug in 1, get out a y value of negative 3. Okay, now we're being asked to determine the value or values of x for when y equals negative 3. So we're saying h of x is equal to negative 3. What's x equal? Well, if y is negative 3, then x can either be negative 4, because if x is negative 4, we get out negative 3. Or if x is 1, we get out negative 3. If x is 1, we get out negative 3. Awesome. Sometimes this is a little bit difficult, so make sure you guys ask questions in class if you don't understand something here. The function notation tends to throw people for curveballs from time to time. The last thing we're going to talk about is the average rate of change. Okay, the average rate of change. So the average rate of change for a function that is smooth, that's key, it has to be smooth, and it has to be continuous. If it's smooth and continuous, you can calculate the average rate of change. On an interval containing 2 different x values, is all this is saying, the average rate of change is given by the slope formula between the beginning point and the end point. Okay, slope of, and I'll draw a secant line for you in a second, in case you don't remember from geometry. But if you have this curve, okay, let's say it goes from here to here, and it can look like whatever, it's smooth and it's continuous. And right here is x1, y1, and over here is x2, y2. Then the average rate of change is going to be the slope of the line connecting those two things, the slope of that red line. Okay, so that's all that average rate of change is. It's really interesting because you can see how this line is going up and then it's going down, it's going back up. So the average rate of change is just clearly here, it's slightly up. Okay, make sure you bring your questions to class. I look forward to helping you.